All right, on to our third example here. Small difference with this example from the previous one. First thing I want to point out, when it's a rational function, one of the things you should check, and I didn't check on the previous example because I knew it didn't already, but you should always factor numerator and denominator first to see if we're dealing with a whole. That's one of the issues that arise when you're dealing with rational functions. So in this particular example, I'm going to go ahead, I'm going to factor top and bottom here just to see what comes from it. And when I do the factoring, on top you get the x minus 3, x plus 2. And on the denominator, difference of squares, x minus 3, x plus 3. Now the x minus 3's will cancel, so the x minus 3's do cancel each other out, but we can't forget about them. So what our function, if I want to go ahead and take the derivative of this function, it's now a lot more simple than it was above. So if I have the choice of taking this derivative versus this derivative, you're crazy not to actually go ahead and do your factoring. So taking the derivative then on top, it would look like this. And the derivative of the second one over the x plus 3 squared. You want to simplify that so I can take the second derivative. Don't forget that this negative sign needs to distribute in, so the signs become negative. That's over x plus 3 squared. X's cancel, so we end up with 1 over x plus 3 squared. So if you look again, and I'm just pointing this out, relatively ugly function to start with, but now first derivative, or sorry, the simplification was easy, and now that first derivative is fairly clean and straightforward, so it allows for an easy second derivative. So it'd be 0 if I keep on with the quotient rule, minus 1 times 2 x plus 3 to the 1, and that's going to be all over x plus 3 to the 4th now. First term's being multiplied by 0. Second term, so we end up with negative 2 x plus 3 over x plus 3 to the 4th. And that reduces to negative 2 over x plus 3 to the 4th. So there we go. We've got our two derivatives taken care of. And thanks to that, thanks to the simplification there, it sure made life a lot easier with taking those derivatives. So I will point out, and I hope people stayed with it and watched all 3 videos or 4 videos. So very, very important to think about doing the factoring. Okay, from that, let's talk about vertical asymptotes for a second, because now that becomes kind of interesting and important. This term that we factored out and canceled out plays a role. So from your MHF4U, you should know that, I'll put it as a star here, there's a hole. If something cancels out, it creates a hole at x equals 3. So there's a hole at x equals 3. All right. Vertical asymptote then, also a VA, vertical asymptote at x equals negative 3. All right, and that comes from the remaining denominator. X equals, x equals negative 3. And that comes from the remaining denominator. So we have a hole and a vertical asymptote in this particular graph. Horizontal asymptote, so we do the check there. So we're doing the limit as x approaches infinity for the function h of x. So the limit as x approaches infinity. So looking at it, x squared is the largest term. So we're going to divide everything by x squared. That's divided by x squared over x squared minus 9 over x squared. So that will become a 1. That'll go to 0. That'll go to 0. That goes to a 1. That goes to 0. So we have a horizontal asymptote at y equals 0. All right, so we got asymptotes and holes taken care of. That didn't sound so good, but anyway. All right, on to x-intercepts. See if there are any. So again, the x-intercept, you let y equals 0. And now we're just analyzing the top or the numerator. So 0 equals x plus 2. I'm going to use the factored form. All right, solving for that, x equals -2. So therefore, at -2, 0, we have an x-intercept. Y-intercept, using my red here, let x equal 0, and we end up with h of 0 is equal to -6 over -9, which is 2/3. So at 0, 2/3, we'll have a y-intercept. And what else do I want to solve for? Max mins. All right, so you're kind of working through your checklist there that you're going to have on the cheat sheet. So my max mins, this is when we let the first derivative, oops, h prime equals 0. H prime of x equals 0. So 0 equals 1 over x plus 3 squared. And you're going to notice that there's no value of x that will make this true. So no solution. Therefore, no solution. Which means, therefore, no max or min. All right. So it's going to make the graph a little bit more interesting for us as we work our way through when there's no max or min. Let's go for an inflection point since we've gone this far. And this occurs when we let the second derivative equals 0. 0 equals -2 over x plus 3 to the 4th. Actually, it should be the 3rd. If we go back in the note a little bit here, not that it's going to affect anything that we've done up to this point, because that x plus 3 would have canceled or reduced that exponent by 1. Same thing here. There's no value of x that will make that true. So you have no solution. So, interestingly enough, therefore, no inflection points. So that means the concavity doesn't change from concave up to concave down during the continuous graph. So at this point, I would recommend let's go and plug in some information here, and we'll go from there. So likely go by singles on my grid. So 1, 2, 3, 4, and 5 on the x-axis. 1, 2, 3, and 4 on the y. -1, -2, -3, 2, and 3, -4. So what do we know? No IPs, no max min. Y-intercept is at 0, 2/3, and the x-intercept is at -2, 0. So there's 2 points on the graph that I now know. Vertical asymptote at -3. So vertical asymptote at -3. Oops. So -3. There's my vertical asymptote. That's a relatively terrible line, so I guess I can actually go ahead and use my asymptote line here. There we go. Now, there is going to be an asymptote at, or a hole at +3. So I'm just going to put in a couple dots here to remind me at x equals 3 that there's going to be a hole along here somewhere. So it's just a reminder at this point in time. Horizontal asymptote at y equals 0. So we'll get the asymptote pen out again. There we go. And remember, some people might be thinking this looks funny, but yes, remember you can cross a horizontal asymptote. So here we are. This is the graph that we're looking at. So I am now running out of information to check or to write down here. So we've got all the information so far plotted. Vertical asymptote and holes there. Horizontal asymptotes up. No max min, no IP, no x-intercept, no y-intercept. So what's it going to look like? So when I'm looking at this, first thing I want to figure out is what's going over here on the left side. So am I going to have a graph that looks like this? Or is it going to look like this? So this is where I'm going to have to do one-sided analysis, or one-sided limit analysis at x equals -3. So I'm going to go back to my rough work page, and we are going to look at end behavior. So I do need some information here. End behavior. And I'm most interested in the limit as x is approaching -3 from the negative side. All right, so the limit as x approaches -3 from the negative side, and I'm using the factored function. Okay, I want to use that factored function, x plus 2 over x plus 3. So now I'm just looking at what's it going to be for a value less than -3. So if I was to put in, say, -4, I would have a negative value on top, negative value on the bottom. Negative over a negative is going to result in positive infinity, because remember, with the end behavior, we're really picking a value that's really, really, really close to -3. But if we pick -3, we'd be dividing by 0. So we're really picking -3.000001. So it ends up being a positive value, which tells me that when I go to sketch this, it's going to exit at the top of the graph. There are no x-intercepts along this part of the x-axis, so it tells me that it's going to, in fact, look like that in the quadrant. So we have that taken care of. All right. Now, I'm looking at what we have left. I want to do end behavior on the right side of the vertical asymptote. Some of you will be already saying, I can predict what's going to happen, but let's go ahead and do the analysis anyway. So I'm also going to do the limit as x approaches -3 from the positive side for this function. So we're looking at the limit as x approaches -3 positive side for x plus 2 over x plus 3. So if we pick something a little bit bigger than -3, so -2-ish, -2 is maybe not the best one, -2.5, because you want to pick something between it and the x-intercept. So -2.5, so the top is going to be negative. However, the bottom now becomes positive. So my result then is going to be -infinity. So this graph exits through the bottom down here. So I need to sketch the remainder of this graph without creating a max or min. So what that tells me is that over here on this side of the graph, it doesn't ever plateau. It keeps continually gradually increasing as it goes out on that side. So what I can do then, I want to find out where that hole would appear to be. So I'm just going to figure out what's the location of the hole. All right. We know it's at x equals +3. So if I analyze or put the value in for my new function here, x plus 2 over x plus 3, then we end up with 3 plus 2 over 3 plus 3. So we end up with 5/6, which is pretty close to a value of 1. So we know that 3 and 5/6, so it's not good. Smart word's off a little bit here. So it's going to be pretty close to that, the whole. So now I'm starting to get the picture. I have a funny feeling it's going to look like this. And it's just going to gradually keep increasing very, very, very slowly. So it's actually walking away from the y or the x-axis, not resulting in any max value there. I paused for 1 second to pull up the graphing calculator just to check my answer. And if you look at my answer, the vertical line there, right there, that's how this calculator represents a vertical asymptote. So we can see that it does mimic the left side of the asymptote's correct. If we go to the other side of the asymptote, it looks correct as well. However, it won't show a hole with the graphing calculator. So anyway, there's example 3 done. One last one. I know it's time consuming, but it is important. You do have to do this if you do take any university calculus courses.